Okay, now we will discuss about the scalar space. So scalar space means, suppose we are considering a sphere. So this is your nx, this is ny, this is nz, this is the center 0 0 0, and this is a sphere. We are taking the part of a sphere. So every particle will remain on the surface of the sphere, on the surface of the sphere. Now if we increase, so this amount is actually your n. This is the magnitude of n. So this radius. So it is nx square plus ny square plus nz square over. So this is actually n. Now this, if this n increases to a little, so how much volume will be increased? So we are just interested in the volume. How much volume will be increased if the sphere is increased a little much? So say this much. So the sphere is expanded by a small depth, small width, del n. So if it is increased by del n, then how much volume will be increased? So this is the increase in the volume, this much. So this is the increase in the volume. So this much is the increase in the volume. So how will you find this thing? So this can be written as, this is called rho of n. So this is equal to 4 pi n square and del n. So this will be simply straightforward writing of this, that how much volume will be increased. So 4 pi n square, that is the surface area of a sphere, into del n. So this much will be the increase in the volume. Now we know that our k is equal to L by 2 or 2 pi by L into n. So this thing, but we want now their del n. So how will we find del n? So n equal to we are getting L by 2 pi into k. So again differentiating, we are getting del n is equal to L by 2 pi into del k. So if we use this thing, and in this place of n, if we put the value of this, then let us see what is happening. So that is called the scalar space. So scalar space is given by, this is the scalar space, so rho of k, and this is equal to 4 pi, and in place of n square we will put this. So this will be Lk by 2 pi whole square into del n, and del n is this thing, that is L by 2 pi into del k. Okay, so what you are getting is 4 pi, and this is L cube by, at the bottom you are getting 2 pi whole cube and k square del k. So now L cube is equal to the volume that we are actually discussing about the volume. So this can be written as 4 pi and the volume that we are interested about, and this is 2 pi whole cube and k square del k. So this thing is called the scalar space. So now we have learned three things. One is number of states, number 2 is the vector space, and number 3 the scalar space. And after this we will discuss about the both scalar and vector space of momentum and velocity. So after doing vector space and scalar space, now we will do that is the momentum. We will do the momentum. Now as we know that momentum is having both magnitude and also direction. So in case of momentum we will have both the scalar space and also the vector space. So momentum is given by P is equal to h at k. Now those who are in class 12 or undergraduate, so they just try to focus it that h hat is actually equal to h by 2 pi and k is 2 pi by lambda. So this 2 pi is cancelled, so this is actually h by lambda. So you have learned this, that momentum is equal to h by lambda. So this is actually de Broglie's wavelength. So as we are considering with here matter wave, so we are considering that momentum is equal to h hat into k. So if we differentiate, then we will get del p is equal to h hat is just constant, and this will be del k. So the value of del k will be equal to del p by h hat. So this is the value. Now if we put this value here, then we will get the vector space of momentum. So this is generally given by, so this is the vector space of momentum. Vector space of momentum is given by G, and this is the P. So this will be V by 2 pi h hat whole cube, and this will be del x. So del kx will be equal to del px by h. So I have already kept h here. So h hat cube, and this will be del px, del py, and del pj. So this is the vector space of momentum, and if we want to take the scalar space, then the scalar space will be, so this will be the scalar space, so rho of p. So this will be 4 pi v by 2 pi whole cube and k square. So the value of k is, so value of k is p by h hat. So this will be p by h hat whole square, and this is the value of del k. So del k is del p by h hat. So again this will give you 4 pi v by 2 pi h hat whole cube into p square del p. So this is the scalar space of momentum. This is the scalar space of momentum, and this is the vector space of momentum. Now we have just used this formula, P is equal to h at k. Now in the place of P, if we put P is equal to mv, then we can also find the velocity space for this. So for velocity space, we have to use this formula, P is equal to mv, or you can say del P is equal to m is a constant, so this will be del v. So if we put it here, then we will get the velocity, vector space of velocity. So this will be the vector space of velocity. So this will be g of velocity vector, and this will be v by, now here you see, so here del p is equal to m dv. So that means this m will come upward. So this is for 1m, another m, another m. So 3m, so m cube. So this will be m cube v by 2 pi h hat whole cube, and this will be del px. In this case it will be del vx, del vy, and del vg. So this is the velocity space. So this is the vector space of velocity, and if we put it here, so we will get the scalar space the scalar space of velocity. So the scalar space of velocity will be p of v. So this is actually written as rho. It should be written as rho. Okay, this is p. So this rho of v. So this will be 4 pi v. Again this is p square. So p square, the value will be m square v square. So m square, and for one del p you will get 1 m. So this will be m cube. So this volume into m cube by 2 pi h hat whole cube, and this is p square. So here you will get, so m square is already taken down here. So this will be only m square, this will be v square. So this will be v square, and this will be del v. Okay. So this one is the vector space, this one is the scalar space, and when you take momentum, so momentum has also a vector space and also a scalar space, and for the velocity also we have a vector space and we have a scalar space for velocity. Now for energy, if we say for energy, so energy is a scalar, so energy will have only scalar space. So in next topic we will discuss just about the scalar space, and that is the energy space. And that is very important, that is very crucial, because all the formulae are related to that energy space. Okay, now we will discuss about the energy space for density of states. So from our previous class that we have seen that the vector space, that the momentum space in scalar space of momentum is given by this. So this is 4 pi volume by 2 pi h hat cube, and this was your p square and del p. So this was the formula that we have got for scalar space of momentum. So this was the scalar space of momentum. Those who have not followed this class, so they are recommended to see my previous class, so they will find this derivation there. And after this, we are what going to do, that we know that P is equal to root under 2m epsilon, where epsilon is energy. So momentum is equal to root under 2me. So if we derive this, so if we take the differentiation of this partial differentiation, so root under 2m is a constant, and differentiation of root e will be 1 by 2 root under e, and this will be del. Okay, so we will use this dp is equal to root under 2m by 2 root under epsilon and d epsilon as it is in this formula, where our p square will be equal to 2me. So let us put this and we will get the rho of energy. So this is the energy state, and energy state will be always scalar because energy is scalar. So this gives 4 pi v by 2 pi h hat whole cube into p square. So the value of p square will be 2me into this thing. So this will be root under 2m by 2 root under epsilon and d epsilon. So now you can see that is 4 into 2, 8, and this will be 2 cube, so 8. So this 8 and this 8 will be cancelled. So these two things and these will be cancelled, and here 1, 2 is there, and this is m, this is m. Okay, so this can be written as v by, this is cancelled, so this will be pi square h hat cube into 2m into m. If we take this m inside, then it will be 2m cube and root e, so this will be root e by 2. 1, 2 is here, so put it here. So into del. So this is actually the energy state of a particle which is moving within any volume. So this energy space is given by rho of epsilon is equal to v by 2 pi square h hat cube into root under 2 m cube into root under e del. So this is very important, and we have to use this thing. Basically we have to start with this thing to find the constant alpha and beta that we have already previously found in case of Boltzmann distribution, classical distribution. So okay, and thank you.